A couple of different videos by Mathologer, StandUpMaths, and Three Blue, One Brown got me to thinking that I could possibly use permutations or properties of iterated permutations to generate so-called random sequences of binary digits. And this is what I came up with. We start with some definitions where we take any set and any permutation of that set and then just count the number of pairs of elements that are in the same order in both the original set and the permutation, and the number of pairs that are in the opposite order. This is the one that mathematicians usually use because that defines the parity of a permutation. If that number is odd, then the permutation is an odd permutation. Uh, People who study ranked order correlations refer to that as discordant pairs or the distance between the two orders. And that's kind of what we're going to use because they use that to form a rank-based correlation. And there's lots of them, but I chose one that's called the Kendall's tau. And it's just the difference between the concordant and discordant pairs and the sum of the concordant and discordant pairs, which in the case of permutations will just be the same as the total number of pairs. And that gives a number between -1 and 1. And the closer it is to 0, the more nearly random the permutation is. Now, if I want to use that to generate zeros and ones, we just say uh, if the tau correlation is greater than or equal to 0, we just give it a 1. And otherwise 0. And if it's an odd if the parity is odd, we give it a 1, and if it's even, we give it a 0. And just for fun, we make up a third possibility that just records whether those two are the same or different. My programming language of choice is Rex, and my favorite interpreter is Regina. So I have started a Regina instance that is executing a program that has some subroutines in it that we're going to use. One permutes a set of numbers or set of any words whatsoever, and one that calculates the distance between two different orders of the same list, and one that we'll get to later that calculates a certain degree of randomness. First, we need something to permute. So we'll just take a list of the first 46 counting numbers, and there's 1,035 pairs and over 5.5 times 10 to the 57 possible permutations, which gives us plenty of room. And we see here that in our sample permutation T, we got 471 discordant pairs, which means that that's an odd permutation, and 564 concordant pairs, and that gave us a very, very small tau value, 0.09 basically. So less than a tenth. So that's a pretty random correlation. Now we saw how to generate a single bit at a time, and the next question is how many bits do we want to generate? And in my case, I want 20 decimal digits. And so we figure out that we need 70 binary digits, and we'll see why that's not 67 in just a minute. This will calculate all of the bits that we need. And so we got our three sequences, one based on tau, one based on the parity, and one based upon whether those two were the same or not. And now the question is, which one of those is the most random? And for that, we use the runs test. And here we see that the parity-based test, this one, is the closest to 0, since with 38 ones and 32 zeros, you would expect by the binomial distribution there to be 35.74 runs, and we actually got 36, which is about as close as you can get. So we'll take the parity-based test and use that to generate our 20-digit decimal number. And we'll convert the hexadecimal value to decimal that we get from converting the binary value of the binary variable to hexadecimal of the one based on parity. And that's a really big number, but we want only the rightmost 20 digits of that. And so that is the random number that we get. The reason I used one more digit than what I was looking for is this. If we just used the power of 2, that would get us 20 decimal digits. We see that the highest number that the first one could be in the first position is 4. So 0 through 4 would show up twice as often as 5 through 9 in the second position there, which is the one that we're taking for our random number. And that we'll just make this a little bigger and say, All right, this is the largest number that we could possibly get from our binomial sequence. And all of the digits are going to show up in that position an equal number of times, basically. So we'll show how this works by calculating 100 of them. And all of this compacted code just saves the file, and we'll open it in Excel and plot those on a scatter plot, noticing that I have divided each of these 20-digit numbers by 10 to the 20 to make them between 0 and 1. And this is what we get when we plot the values sequentially. And that looks pretty random. Let's do another kind of test. We'll find the r² value. And that is 0.0081, which is pretty good indication that this is a really random scatter plot. And if we notice, the average value, apparently I didn't include that in the capture, but the average value is 49.495, which, if that was a completely random sequence, we would expect to be about 0.45 or 0.5. So we did fairly well, I would say. I actually made something useful out of this. This is a page that has 100 20 by 20 squares of random colors, where I just generated 24 random bits using the same thing. And if I click on one of the squares, I get just a single little square. And what I can do with this is exercise my printer so that I don't have to clean the print heads, because I don't always print colors. And I can use one piece of paper front and back to do 200 weeks worth of regular exercising the print heads. In short, this is kind of what random looks like. We've done it with numbers and with colors, and I hope you enjoyed it, and I hope this works better than my last one.